hear me? Yeah. Okay. So I'm going to talk about hopefully not too obvious talk, and so please feel free to comment and interrupt. I'm going to talk about nonlinear effects in modified gravity. So here the idea is that one of the perhaps not obvious results that may be coming from future surveys is that the cause of acceleration of the universe may be modifications of gravity at large scales. And so far, I think it's fair to say that all of the treatments in the literature assume that this modification of gravity can be described linearized by a linearized modified Poisson equation. And so what I want to show in this talk is that that may not be a very good assumption. And in particular, if you are talking about gravitational lensing, there may be some non-linearities in the Poisson equation that have to be taken into account. So first, a few general comments about modifying gravity at large scales. General relativity is an extremely constrained theory. It basically follows from having a massless graviton plus general covariance. So any modification from it, from fundamental theory, implies that gravity cannot be mediated by a massless spin-2 particle. So new degrees of freedom are expected. So that means that just taking the Poisson equation with just the potential and modifying it phenomenologically, it's not really a good path to take. So really you expect to have new degrees of freedom showing up. I'm going to discuss a particular example where that's the case. And everything can be calculated. So as I said, most modifications will lead only to additional scalar degrees of freedom. And in that case, you have to be careful about solar system constraints because the scalar degrees of freedom, if they remain alive at solar system scales, they will violate solar systems. So somehow you have to suppress these additional scalar degrees of freedom at small scales. And the way that shows up in cosmology, it's interesting. So that's basically the topic of this talk. Sometimes people distinguish just modifications of gravity in general that only modify scalar degrees of freedom. So in some sense, they are equivalent to quintessence. But there are so-called true gravity modifications, which also changes the spin-2 sector and lead to new polarizations of the graviton. And this also has other implications from gravitational waves and so on, which I'm not going to discuss in this talk. So, so as I said, we expect new degrees of freedom at some range of scales. Typically what happens at scales where you can linearize the theory, you have additional degrees of freedom, which are scalars. In order to avoid solar system constraints, these scalars must be suppressed at small scales. And in cosmological settings, the way this is suppressed is in some class of theories, at least, is typically done through nonlinearities, which is something new that GR doesn't have. And this leads to many observational signatures, some of which we'll discuss here. So the example I want to discuss is the so-called brain-induced gravity. The reason, this is sometimes called the DGP model, the reason for it is just to give, it's an example where everything is calculable with as many free parameters as lambda CDN. So it's a very predictable theory, except that making the predictions is quite a bit more challenging than in the lambda CDN case. So in this case, Einstein equations, we live in a the universe is actually 5-dimensional, 4+1. We live in a brain, which is 3+1 dimensions. And so here we have the Dirac delta at the brain. So this will be the standard Einstein equations. And there is an additional term, so-called bulk term, which is essentially gravity, 5-dimensional gravity, suppressed by some scale RC. So this scale is actually the scales that at which gravity goes from 3 plus 1 to 4 plus 1. So this is a scale which is usually over the Hubble scale to explain the acceleration of the universe, as we'll see in a second. So if you look at these Einstein equations in this theory, they have exactly the same numbers of free parameters as in lambda CDM. In lambda CDM we have lambda. In this theory the only free parameter is this crossover scale, RC. Okay? And if you do just dimensional analysis, you can just, let's take a point source in our brain, and any metric perturbation is just phi. So this equation is just phi, you can write it as phi over RRC. This one is phi over R squared, because you have second derivatives. And here is a source, 1 over R cubed. So you see that at small r, this term becomes much more important than this. So phi goes as 1 over R, that's just a Newtonian potential. When R becomes comparable to RC, this term takes over. And at very large scales, this term dominates over this, and so phi goes to 1 over R squared. That's the 4-dimensional spatial behavior for a potential when 5-dimensional gravity becomes important. So this RC is just, instead of being the, if you compare with lambda CDM, instead of having a lambda, you have this scale at which gravity becomes weaker because it becomes 5-dimensional. And that explains the acceleration of the universe, as we'll see in a second. Or at least has self-accelerating solution. Okay, so I'm going to tell you a little bit about what are the differences from standard GR. You can write the metric perturbations in this theory. So the first two lines are the usual ones in 3 plus 1 universe. So we have time and coordinates here, spatial coordinates. So the usual metric potentials, phi and psi, A and B. And then in additional, we have this last line, where W is the extra coordinate that we have now. So we have 3 additional scalar perturbations now. So the background evolves in a simple way, as we'll see in a second. So this alpha and beta just characterize the background, the evolution of the background. And the equivalent to the Robertson-Walker solution, Friedman-Robertson-Walker cosmology, this alpha and beta are given by this. Remember, W is the distance away from the brain. So when we are at the brain, e to the alpha is just the scale factor, e to the beta is 1.
Robert,
yeah.
Question about the Einstein equation. So usually people do either a junction condition and project 5-dimensional gravity to the brain. Are you doing this?
No, as we'll see in a second, I'm going to solve the equations in the bulk and in the at the brain without projection. You could do it.
So in other words, you're working in 5 dimensions.
Yeah. This will become obvious in a second. So as usually in GR, you have, so now instead of having 4 metric perturbations, usually in GR, right, you have 4 metric perturbations. You can kill 2 scalars, typically, and the Newtonian gauge, you just kill these 2. And then if you have an energy momentum tensor with no anisotropic stress, then phi is equal to psi, and then you're left with just 1 metric perturbation. So now instead of 4, we have 7. But you can show that there is I'm going to work in a gauge where it's the usual gauge for Newtonian gauge, A equals B equals 0. You can show you can also set this metric potential equal to 0, and the position of the brain, even when there are perturbations, you can also set to 0. So once you do this gauge choice, you are left with 4 metric perturbations, the usual 2 in GR plus additional 2 scalar potentials. So let's first do the evolution of the background. So if you write the Friedman equation, you see that the Friedman equation takes this form. So now because you have modified the left-hand side of the Einstein equations, the dependence on the Hubble constant becomes non-trivial. So if I put this term actually belongs to the left-hand side, I can put it on the right-hand side. And you see that now, as the density goes to 0, the solution of this equation is Hubble equals to 1 over RC. So it has a constant Hubble exponential de Sitter expansion with a Hubble constant, which is 1 over RC. So as the universe, as the density in the universe washes away due to the expansion, you enter de Sitter expansion with this Hubble constant equals to 1 over RC. So this crossover scale actually gives you the asymptotic Hubble rate expansion. We are not quite at de Sitter. If this theory were correct, we are not quite at de Sitter yet because this term is not completely negligible compared to that. So you can write the acceleration, and if I'm useful time variable to choose is h times RC, which is dimensionless. So in the early universe, eta is very large. Today, eta, in order to fit supernova more or less, this eta will be of order 1.2. So the scale factor when in the early universe, when eta is large, evolves as essentially t to the 2/3. When eta gets close to 1, then this shoots up and you have a de Sitter exponential expansion. So I'm going to work, you will see the equations appear in this combination, which is the acceleration parameter instead of the deceleration parameter that people use. I think it's about time we change the sign. And we acknowledge the universe is accelerating, so I'm not going to put the minus sign here. So, and so in the de Sitter limit, when you run out, the density goes to 0. H is equal to 1 over RC. So eta goes to 1. The acceleration parameter goes to 1, and you have the Sitter expansion. Okay, so this is about as far as I will discuss. You can think of this, if you want to parameterize this as a dark energy, you can find an effective W, which is time dependent, and the effective W is minus 1 over 1 plus omega matter at a given time. So in the early universe, this will behave like a W minus a half theory. At late times, it behaves like a minus 0.8 or something like that. Okay, so how about perturbations? So I'm going to assume just T mu has dark matter, is just dark matter with no anisotropic stress. So one of the constraint equations says that this metric perturbation C, which is usually called the brane bending mode. So the idea is that we are at the brane, and if you put source there, this brane will bend, okay? Just due to gravity. And this C roughly measures in some gauge, which is not the gauge I'm taking, but doesn't matter. This bending of the brane is described by this metric perturbation C. So you see that if I take RC to infinity, right, which will be one way of reaching GR limit, so this C over, as long as C remains finite, this C over RC will go to 0, and you recover phi equal to psi, which is the usual thing in GR. So the fact that this brane bending mode is not 0 will give a mismatch between phi and psi, which will become important, very important in a second. So when you see a 0, it means I'm looking at equations at the brane. So this is the Poisson equation that you get from this theory. So quickly, the right-hand side, this is the usual thing, just the density perturbations. This is also the usual thing you get in GR, which I'm going to ignore. So these are the terms which we usually ignore at small scales because Laplacians are much larger than this. So I'm going to ignore these terms of what follows. This is the usual term in GR also. This term, if I take RC to infinity, these two terms will disappear and we will get the standard Poisson equation, right? So the new ingredients here is that there is this extra degree of freedom, this brane bending mode, okay, which you see is related to the mismatch between these two potentials. And then this we'll see later, this becomes negligible. The other non-trivial term is these normal derivatives to the brane. So derivative prime is a derivative with respect to the W coordinate. And so we'll see that from the 4D point of view, this term introduces very non-standard behavior compared to four-dimensional physics. So going back to what, yeah.
C here is the time picture dimensions.
Yeah. Extra space.
Always space.
Yeah. Yeah. So it's essentially, if you do ADM, it's like is the shift vector. So it tells you how one hypersurface is shifted with respect to the other. Okay, so going back to what Lev was asking, you see, you notice these equations. If you want to solve these equations, right? So I'm going to neglect this term, as I said. So I have 3 metric potentials, and I have 2 equations, right? Plus I have this normal derivative, which I have to evaluate. So in order to close the system, you have to match what happens at the brain, which was in the bulk. And so I'm not. This gets a bit too technical, so I'm just going to sketch how you do this. The easiest way, which is one of the new things I've done, is the easiest way to solve the bulk equations is to decompose these scalar perturbations into 2 classes. Essentially, the idea is we want to separate what's the physics at the brain from the physics at the bulk. And to solve these coupled equations, to decouple them, you decompose these 4 potentials into 2 potentials and 2 which are invariant under shifts of the brain position. So if I change the position of the brain, this potential and this potential, you can show they are gauge invariant. Okay, so these guys describe what's going on at the brain, essentially. And then ones which are not invariant, which is the brain bending mode, and this combination 2 psi minus phi, which is what essentially is the richest scalar at a given hypersurface, like the brain. So there is a physical interpretation for this. So I'm going to skip how you solve this, but my claim is that after doing that decomposition, you can decouple the equations. And so we are here, I'm plotting here now how these solutions behave in the bulk. Okay, so we have at S equals, so this is the extra coordinate times Hubble constant, so it's a dimensionless number. And so we are here at 0, and we put some density perturbation there at the brain. And you see that the 2 perturbations, which are 2 variables which are invariant, they are, so this one is negligible, it's very small at the brain. But this one, which is the relevant one, it's concentrated at the brain, and that's why it's gauge invariant, describes the physics at the brain, and then it decays exponentially. And this is for 1K, this is for a higher K mode. So you see the higher K mode, the more concentrated at the brain it is. So these potentials decay, this is what usually we mean by leaking gravity into the brain. They are localized and they decay to 0 very quickly. Whereas the potentials which are not invariant, they describe the physics in the bulk, and they do not decay to 0, so they are fairly constant into the bulk. So you see that if we remember, if you go back to the Poisson equation, what we need to evaluate is, for example, this normal derivative of the brain. You can see from this behavior that the normal derivative is going to be dominated by this potential, which is a very steep derivative at the brain. So that will introduce a very non-standard behavior. So after some massaging, you can convert the effective Poisson equation, where I threw away the relativistic terms on the right-hand side, as I said, because we are scales well within the Hubble radius. You again have the standard Poisson term, the contribution from the brain bending mode. And then this normal derivative, you can show that you can write in terms of 4-dimensional physics as this very strange looking non-local operator. So this will be in Fourier space K times phi 0. So you will never get such a term from 4-dimensional physics. So this is, if we see something like this, will be an indication that gravity has been modified by extra-dimensional theory. And so these kind of terms are actually the ones that control the behavior from 4 to 5D at very large scales. So because they have one less derivative than this one, they dominate at large scales. So after some massaging, you can write this as effective Poisson equation in terms that cosmologists can use. So here is the Laplacian of the gravitational potential now equals the standard Poisson term with some time and scale dependent modification here. So eta, remember, is the time variable, is h times rc. Q is the acceleration parameter, and k, this is a combination physical k in terms of the rc And so this term is actually coming from this k-dependence is coming from this non-local operator. So you can put everything into a G here and call this effective modification of Newton constant, which is scale and time dependent. And then you can solve the linear growth factor just by doing the usual thing we do in GR. And so what you see is the following. So if it's just the usual GR equation, but with a modified Newton constant. And this again is a statement that at these scales, the theory is just the equivalent to the additional of a scalar. And so if I look at how this effective Newton constant is in terms of G, so I high redshift, this goes to 1, so there is no modification because the scales are relevant scales as much smaller than this RC, which is Hubble today. So at high redshift, the theory goes back to GR. As you go forward in time, you see that the extra scalar suppresses the growth of perturbations, and because the reason why it suppresses is because you can show that this additional scalar is 5 minutes. Should hurry up, okay? This extra scalar is repulsive, so so it suppresses the growth of perturbations, and then you see this suppression at enhanced suppression at large scales. That's when the theory starts to go 5-dimensional. Okay, so when you get to redshift 0, the effective Newton constant is about 70% or even less than in standard GR. So this means that the growth of perturbations is highly suppressed compared to lambda CDM, or compared to any GR-based model with the same expansion history. And if you can do the growth factor from this, so this is growth factor at redshift 0, 1/2, and 1. So you see the effect is not as strong as in the Newton constant because this is an integrated over time effect. Okay, so this is all linear. Okay, so what happens when you include nonlinear effects? If this extra scalar was present all the way up to small scales, this theory will be in complete conflict with the solar system test. And so the way this theory and a class of theories evade these solar system constraints is through nonlinear effects, which suppress the scalar mode at small scales. But because there are nonlinearities, as usual, leave other signatures as well. So you can tell what's going on. And the phenomenology of this is much richer than in the case of GR. So I'm going to sketch essentially how you do the nonlinear case. So the important equation here is an equation that relates this brane bending mode to the, remember these are the standard, these gauge invariant potentials which are related to phi and psi. So this is the usual, so because nonlinear effects become important at high k, this only has one derivative, so you can forget essentially about this term. This term is the usual thing, is the Laplacian of this potential, which as I said is essentially the Ricci scalar, which is of order delta for density perturbation. And so this is a nonlinear equation. You see once you put nonlinearities, the right-hand side is the nonlinear term that appears, which describes that this brane bending mode, C, becomes nonlinear. This contribution becomes comparable to this at some scale. Okay? As we'll see, this nonlinearity actually works in a rather remarkable way compared to GR. When nonlinearities become important, you think that the theory becomes, this degree of freedom becomes relevant. So here we will see that nonlinearities have the effect of switching off this mode. So remember, this C naught is the mismatch between phi and psi, right? So if C naught somehow becomes suppressed, then you recover GR. And that's how the theory survives solar system tests. And so because this, I'm going to sketch how this switching off of this degree of freedom happens in the following way. So here we have Laplacian of C, here we have essentially Laplacian square, here we have delta, and we can forget about this because we are talking about high K. So essentially, schematically, this equation says you can write it algebraically like this. The relevant degree of freedom plus its square is equal to delta. Yeah?
How come the only nonlinear terms involve C? Why are there other nonlinear?
Yeah, you can show all the, by doing power counting, this is the only relevant nonlinear term.
You mean having K, power K?
Yeah, yeah. So schematically, the equation looks like this, okay? So we see something very interesting happens. So suppose we are at large scales. At large scales, delta is small, okay? Density perturbations are small. So how do you solve this equation? Well, it's very easy because the solution is that the balance for delta happens in the first term. So if the first term is over the delta, the second term is over the delta square, which is negligible because delta is much smaller than 1. So at large scales, this guy becomes over the delta. This is delta square. We can forget it. That's the solution. So again, this means that in the Poisson equation, you have this term, right, which shows up here, is of the same order as this, and that gives you this effective modification of Newton constant that I just described in the linearized case. However, when delta becomes of order much larger than 1 at small scales, the opposite happens. Because now the solution of this equation is to say this guy now balances delta when delta is much larger than 1. Because if this is over the delta, then this guy is over the square root of delta. And because delta is much larger than 1, this is much less than delta. So now this is negligible. So when you go to small scales, this brake-bending mode now is over the square root of delta. So that means that if here, this is over the square root of delta compared to delta, you can neglect this and you go back to GR. Okay? Yeah?
Oh, the free mode, 1 over R, the solution for delta equals to 0.
What?
What about the free mode, the 1 over R?
No, okay, you can this equation you have to solve this equation too. Yeah, this C equals 0 will not be a solution once you have everything here.
So how do I calculate?
Because this is a non-local equation, right? Yeah.
But shouldn't the Poisson's equation also have nonlinear terms in the
Yeah, but all the way nonlinearities happen in this theory is that all the nonlinearities that appear in this equation are negligible. The only nonlinearity that is relevant is the one that relates this guy to this guy. Okay, I'm not showing that. You have to.
Negatively in the sense of in the high K limit.
Yeah. I think that's true generically. Well, nonlinear terms are important in the high K. Okay, so let me now sketch how the theory approaches GR and what that means for predictions, for cosmological predictions. So the idea is that the idea is a linearized Poisson equation, which will be this one, will be relevant at large scales, where this is the same over that, and then you're linearized, and it will be also correct at small scales, where you can neglect this, and this is linearly related to delta. But it's not true in between. So you have the remarkable situation where the linearized Poisson equation is true at low k and at high k, but it's not true in between, where you have this complex phenomenon of switching off this extra degree of freedom, and that's due to nonlinearities. And so the relevant question for observations is, where is that scale? Yeah.
Yes, exactly. So where is that scale?
Yeah, I'm going to show that in a second. Okay, so how you solve this is kind of complicated, and I cannot explain this in much detail. But the idea that of how you solve this is by you can write the Poisson equation. So if there is no modification of gravity, the right hand side of this equation will be 0, right? So this is 4 pi g a square rho bar, and the right hand side will be the modification of gravity enters through this term. So in the linear case, m at k goes to 0, m goes to 1, so you get an extra contribution to delta, and that's the modification of gravity. as you go to high K, this guy goes to 0 and you recover Poisson. So this guy is actually encodes all the nonlinearities. Okay? And the way, because this theory, nonlinearities become important, you cannot really use perturbation theory. So you have to use some kind of resummation in order to describe this asymptotics of this nonlinear term. So, so what I have done is to do that in some approximation, and here is the result of what implies for the effective Newton constant. You can describe this as some effective Newton constant again. And here shows now what happens at redshift 1 and redshift 0. So remember, this is this is the linear approximation that I showed before. Okay, this is redshift 0. This is redshift 1. And the solid lines describe how the theory, when you include nonlinear effects, how the theory switches off. It kills this extra mode, and G goes to 1 at small scales. Okay, so you see that the scale of the transition where the action is going on is at scales which are very relevant for observations. So for example, here is variant acoustic oscillations, weak lensing. So there is a danger of using the linear approximation for the Poisson equation when you're actually making predictions for observations.
Well, it's just changing the G for the deflection of light as well as the G for the growth of structure.
Yeah,
Same.
it's G is somewhat different. Because what enters for deflection of light is phi plus psi, but they are related. They are related. So you will see a similar behavior.
I'm a bit confused about this. So you're saying that essentially we have very nonlinear system with this crossover scale, and you're still describing it in Fourier space. So how does that work? Fourier is linear combination of stuff. So can you really do description in Fourier?
No, it's actually, there is a lot of abracadabra from going from here to there, which I'm skipping. But there are some, in order to make it local, you can make it, under some approximation, you can make it local in real space. And then you can Fourier transform back. And this is the result. So we can talk more later if
Are you using all of the machinery of resummation?
there is some similarities with resummation in renormalized perturbation theory. So the idea is that because clearly these nonlinear terms, you cannot really solve this equation because these are random fields, right? So you have to give me a density perturbation in order to solve it. So the idea is to solve it in some average sense, like in a propagator sense, like we do
it for usual.
Yeah, and so you try to solve this for a typical spectrum, and then what enters in this equation is the spectrum and bispectrum of density perturbations. Okay, so just to finish, conclusions coming next. The bottom line from this is that you should be worried about just using linear Poisson equation to make predictions. What happens at small scales, in particular for lensing, when you're dealing with modified gravity theories. Because if modified gravity theories survive at solar system scales, they have to suppress the scalar modes, and one of the general mechanisms for doing that is nonlinearities. So nonlinear effects will maybe importantly at the scales you're looking at. And the nice thing about this theory is that everything is determined, right? There is no free parameter. It's like lambda CDM. So you tell me omega matter today, and I can make this prediction. In order to do the same for other theories that show the same behavior, is much harder because they usually have many free parameters, and then where this scale is, depends on the choice of parameters. So the nice feature about this theory is that this prediction is essentially there. Okay, so let me conclude with some future work. As I said, I try to stress the effective Poisson equation, maybe nonlinear at the scales we are proving with cosmology. Next step will be a reliable calculation of the nonlinear spectrum, which takes into account this effect. In particular, we want to see what's the impact for variant acoustic oscillation experiments and weak lensing at smaller scales. Something I didn't have a chance to talk about is that You can use, as usual, if there are nonlinearities, you can use higher order statistics, such as the Y spectrum, as a diagnostic for extra nonlinearities which appear when you modify gravity. And as I said, I try to stress and say it again, using linearized modified Poisson equation is probably not a good assumption, especially for weak lensing, so it's something that you should keep in mind. Okay, thanks.
Any questions? Matt?
Delta T over T and logical structure. You know how delta T over T will be?
Delta T over T is in a regime where the linearized approximation actually works very well. And that has been done by other people already.
Yes, but we not specify have initial almost scale 3 power spectrum. Output will be some alpha delta T over T and correlation in power spectrum for galaxies. Will they be compatible with everything?
Say that again, I didn't.
So you can calculate delta T over T, CITA, usual thing.
Yeah.
But for this model, so you say for it will be undistinguishable from cosmological constant.
No, it's not undistinguishable. So there is a modification.
Good. But what about power spectrum for gravity, for galaxies?
Yeah, so for galaxies, as I said, the growth factor is much smaller because this extra scalar mode is repulsive.
Did you compare power spectrum with the data?
No, not yet, because the nonlinear effects have to be taken into account to properly do that with data. But my guess is that there is enough evidence already that this particular theory does not fit the data very well.
Okay.
So I'm not, but this is an example of many. There are many. Any generic modification of adding invariants to the action will have the same properties that I described here. The problem with those theories is that they have so many free parameters. It's hard to make a robust prediction. So that's why I use this particular case.
I'm still a bit confused about this G effective parameter. If it's like, is it like an ensemble average of something which would vary within space? Like if I need to have G in galactic cluster or within galactic cluster environment, or if I have to use it in a big void, would it be different?
Yes.
So I should think of it like a bracket thing.
Yeah. So at the linear level, no, it's the same everywhere. Well,
Yeah.
with some scale,
Yeah,
scale dependence.
initial calculation you presented.
Huh?
The initial.
Yes, the initial one. The nonlinear calculation, yes, is an ensemble average. In ensemble average sense.
Okay,
So-
so it's only valid for P of K, basically.
Yeah, exactly. Yeah.
Robert, do you also expect consequence from the kinematics of clusters of galaxies on the scales of megaparsecs and tens of kiloparsecs?
Yeah, so there will be some modifications there. But by that time, the theory is close to GR, but with a different expansion history. So it will, Hubble constant is different in terms of density. So there will be some modification, but it will be kind of smaller. And my point is that people usually leave the Poisson equation linear, and so then you will predict like a strong modification at this case, which I don't think is true. So it makes things a bit harder.
Right. Any more questions? Terry?
Well, you mentioned that there are observations that claim to or come close to ruling out DGP, but I think those are ISW kind. Is that the main one?
Yeah, the supernova already, even supernova alone already
Okay.
put some tight
So
constraints.
the supernova, that's expansion history, that wouldn't be affected by this.
No.
But would the ISW constraints have to be reconsidered?
No, I don't think so
It's
either.
large enough scale.
But usually when the strongest claims that people make about DGP is adding BAO, then really the theory is ruled out. And then I don't think you can do it because of these concerns.
So you would discard the BAO argument
Yeah,
against DGP right now.
exactly. Yeah.
All right. Time for one last question. No? Yep. No?
Mine is in the end, your prediction for the linear growth factor is then possibly to go home with that after
Yeah.
that's the same.
Yeah, the only thing that is new is when we did this prediction 4 years ago, we neglected the normal derivative, so we don't have the transition to the 5D regime, and that's pretty That's so what we had 4 years ago was essentially this line being a constant. Okay, and what I'm saying is that that's almost never a good approximation, right? Because it does something like this.
But for the growth factor, it's probably
For the growth factor, it's better than for G, of course, because it's a time integrated thing. Yeah, it's much better actually than what is in here.
All right, let's thanks Roman again.